Yep. Yeah, should work. Yep. Thanks. Hmm? It's always a little bit tricky with these. So, okay, yep. Will you start the
Yes.
presentation? Okay, yeah. Sure.
Just to check the slides that they are actually the current version.
Okay.
Check only that they are working.
We can just confirm your last version.
Yeah, I think so. May I quickly... yeah, this is... Sure.
There were lots of fire. Yeah. There were several wallways. The last version. Yeah. Your last. I did check it earlier. Yeah. You okay about yeah. Sorry. No, those are completely wrong. You have no idea how much is there. I knew you have to.
Do we have to switch slides directly at the computer, or is there? No. I mean, to switch forward the slides, is it directly on the computer, or is there this little remote control thingy? Yeah, I know that one. Yep. Yeah, don't hurry.
Well, there was a whole project. But that's okay. We have lots of money. Right.
Good morning, everybody. So, my name is Otto Kreiter. I'm the chair of this session, and we will talk about the transport networks. And we have here actually 3 prominent vendors to talk about the challenges in the DWDM networks and how they are working on that. And I would like to invite first Dr. Klaus Grob to talk about advanced challenges. I'm not going to introduce all his nice work because it's quite a long list, but he has more than 20 years experience in DWDM, and I'm sure he will be able to tell us quite a lot. Please welcome Klaus.
Thank you. Morning, everybody. Okay. So welcome to my presentation on next generation of ultra-high-speed WDM transport. What I want to do today is give an outlook on what may come after 100 gig. So yesterday in the evening, for those who attended, I mainly spoke about 100 gigabit, and now that's the a possible next generation. So this is the outline, 1 or 2 slides on coherent 100 gig technology, just to remind you how it will look like. Then what we call software-defined optics as an option for ultra-high speed beyond 100 gigabit transport. And also 1 or 2 slides on optical layer switching and its requirements in order to properly support ultra-high speed transport. So this is one of the slides I showed yesterday in the evening. Just a little bit of history and possible future. So what did we do up to and including 100 gigabit? 10 gigabit, of course. That was on-off keying, which is basically intensity modulation. So in the constellation diagrams, I have 0 for, well, no intensity, and plus whatever, 1 or A or B or something for intensity, laser switched on in a somewhat simplified way. That also used direct detection. It typically did not make use of any polarization states, and hence the systems also needed optically compensated transmission lines, that is dispersion compensation along the lines. With 40 gig we had a mixture. Most of the systems were still, well, self-coherent or non-coherent. That means, for example, differentially detected phase shift keying, and also at 40 gig we saw a first system which made use of the technology that we are now going to use for 100 gig and whatever comes next. That is digital coherent intradyne systems that do make use of polarization multiplexing and more or less massive DSP processing at the beginning for the receiver, for the receivers, for the polarization demultiplexing, for the equalization or dispersion compensation, but which will over time also be used in the transmitters. And what I will talk about in this presentation mainly is what may come here in this arena: 400 gig, 1 terabit. Well, beyond, I can't say. I don't want to look for more than 10 or 12 years into the future. Another recap: the block diagram of a coherent 100 gigabit long-haul transport system, and luckily they will almost all look similar, so they will make use of polarization multiplexing. That is, the transmit laser is split into both polarization planes. Both are modulated independently by means of IQ modulators, and the receiver, in the receiver we split the signal into 2 arbitrary planes of polarization, mix them with a local oscillator in passive 90-degree hybrids, detect them in typically at least in 4 balanced detectors, or receivers, and then deconvert them and do the rest in the digital domain. The rest is the complete dispersion compensation, the polarization demultiplexing, the polarization, the PMD equalization, and possibly also nonlinear mitigation. And by means of this, the systems do have more or less the same reach capabilities of standard 10 gig. They may on brand new fiber plant even exceed, and on old fiber plants in particular, if they are inline compensated, they may not achieve their maximum reach for several reasons. We have good spectral efficiency due to both the polarization multiplexing and use of QPSK. That is a 4-state modulation, as shown on one of the previous slides. And the standard chipsets from the main chip vendors, they will become available more or less during this year. So they are a bit delayed, which has to do with the fact that this, from the electronics point of view, a quantum leap. We are now talking 40 nanometer CMOS, where a typical receiver here has to process approximately 1.7 terabit per second in real time. That was simply absolutely impossible 3-4 years ago. So this is it, the digital receiver. It consists of several stages. First, of course, the ID conversion. Then, and that is pretty interesting because it almost reverses the order of processing compared to an old-fashioned analog coherent receiver. First comes the digital equalizer for chromatic dispersion and possibly also nonlinearities. Next, clock recovery, that is alignment of the sampling with respect to the baud rate. Then the polarization, demultiplexing, and also PMD equalization. For QPSK, so for 100 gig, in most cases by means of the constant modulus algorithm, which is simply a special algorithm who does the work. An unmodified CMA, for example, wouldn't work for 16 QAM. You need to do something then, but other algorithms could be used for whatever QAM. Next comes carrier recovery or phase recovery, and this is the interesting thing, because that would have been the first task in an analog coherent receiver, and then the decision. And as I said, this whole structure has to process approximately 1.7 terabit per second in real time. And for example, one of the chromatic dispersion compensation stages, in dependence of how much dispersion you want to be able to compensate, may already have more than 100 taps in a linear FIR filter. And then the filters that are used here for polarization demultiplexing, they must be fastly adaptable, because obviously polarization state can rotate. So these are further FIR filters. The whole thing can be done with or without feedback. So there are many possibilities for the implementation of the DSP. But the general structure of the dual polarization QPSK system, or even dual polarization QAM, remains, and that is the good news. Next, 400 gig or maybe beyond. Why? Well, why? Data rates are increasing. We saw it the last 20 years. It depends where you look, but it is approximately 50% per year. We do see it in the access, we do see it in the backbones, we see it more or less everywhere. In processor capabilities, by the way, as well, of course. Also, maybe, possibly, hopefully, to reduce the number of managed entities. But mainly, I guess, because simply data rate is increasing. And for the remains of this slide set, there are some assumptions. For 400 gig, we assume a line rate of 480 gigabit per second. That is 20% overhead for FEC. Similar for 1 terabit. Isn't it 20%? I think so. We assume, because for the ultra high speeds we may need more than one carrier, what is called Nyquist WDM, that is the total bandwidth of all the carriers or subcarriers equals number of subcarriers times symbol rate. We assume, yes, massive simplification only in AWGN channel, that is only added Gaussian noise. To a certain extent, we assume nonlinearity because we say, well, let's keep the total power over all channels constant. This is okay because it either leads to compliance with laser safety, or at least we limit nonlinearity. That's good. And for the upcoming flex grid, flexible RODM grid, for those who attended yesterday's workshop, they know what I'm talking about. But there is one slide at the end. We assume a granularity of 50 gigahertz, and then what can be okay, and then we need to notice we run into at least two fundamental limits. The one is I can't say that FEC will ever give me more and more coding gain. That it does not. We with an implemented FEC of approximately 11 dB net coding gain, we are close to Shannon limit, and we can't add more and more overhead, because then the trade-off starts with the increased baud rate, the increased effort for compensation, etc., etc. So we have to limit the overhead somewhere in this region, and we will never exactly achieve the theoretical limit. So we are already close to the limits with the FEC, and it's even worse with regard to total capacity. This comes mainly from a famous, really good paper from Bellabs, from Egembre and his co-authors, who showed there is fundamental total capacity limits in fibers, and we are unfortunately already more or less within a factor of 10 of this limit. So don't expect that we in 20 years we can 100-fold the capacity of our 100 gig systems. That is not possible on your fiber plant. You would need completely new fibers, completely different fibers. And what we see here is, yes, theoretically I could increase total capacity of a fiber more or less without limits by going towards higher order modulation. And higher order modulation obviously needs higher system to noise ratio, because the distances between all the symbol states excuse me, decrease. And exactly that is not possible, because fundamentally the fiber is a nonlinear channel. And if you increase, that can be seen here, if you increase the SNR by increasing your power budgets, you run into fundamental nonlinear limits. You see it here, that in reality total capacity of the fiber would decrease again. So we need to find somehow these optima, and we are pretty close to them with the coherent 100 gig systems already. So, and that by the way also means we would not increase total capacity by switching onto, say, 64 QAM to 56 QAM or whatever that is, and maintaining, say, 2,000-3,000 kilometer transparent reach. That already is impossible. And it's maybe not necessary, because total capacity in many applications depend on reach. In other words, the shorter the reach, the higher the required capacity is. They are inverse proportional in many, not in all, but in many applications. And that is good, because that leads to the concept of, flexible transceivers, or what we say software-defined optics. It is purposely chosen the name, of course, to remind you of software-defined radio. Similar concept, by the way. And it means software-based configuration or implementation of operating functions, not software control of whatever set points. That is done already. That's clear. It really means software-based implementation of modulation schemes, for example. And that means with one and the same transceiver, I could switch from QPSK or 4 QAM to something weird, if you like, 36 QAM or 49. Why not? They all can be used, and still it is based on the same hardware, and that is relevant. We don't end up in the chaos of 40 gig. It is one and the same piece of transceiver hardware. And then, having the assumptions in mind, there is several options, not necessarily complete the list, of course, just to give an idea of what could be done for 400 gig or 480 gig. We will end up with likely several subcarriers. There is options for one subcarrier, but if we consider, for example, single carrier dual polarization in every case, 64 QOM, we end up with an incredible penalty against coherent 100 gig systems. And this is also in 50 gigahertz. Now, if we choose single carrier 16 QOM, we end up with 100 gigahertz. So there we already need an option for a flexible grid, but here we have a much lower penalty. Why is that? Because if we allocate 100 gigahertz, we have less channels, and since we keep total power constant, the per channel power increased, and this gave us some dB back. So the broader the bandwidth is here, the less channels I can transport, say, in the C-band, and since I keep total power constant, the higher can the channel power be. This is considered in these penalties. These are the absolute penalties that we would see in the end. And if we now draw a curve with constant capacity times reach, this is typically the relevant parameter in transport, that it goes like this. We see that our coherent 100 gig is more or less optimum already with regard to capacity times reach. And that most of the proposals here are even worse. We could do something exotic, like not using dual polarization, that is polarization multiplexing, but something that we call polarization, or that is called polarization switching, where I don't modulate the two polarization planes independently, but where I do see them together with I and Q as a four-dimensional symbol space. And modulate them dependently on each other. That would even give us a dB or so, but you can see that with the 100 gig system we already write the optimum curve, and that there is some contenders that are better than others, and certainly they have different reach and different bandwidth, and that also leads to the requirement of flex grid. Similar thing for 1 terabit. I won't go into much detail. Same concept here. With the difference, we end up with more. Okay, we end up with more. Certainly with more subcarriers. It is doubtful that 1 terabit will be done with a single carrier. And we didn't, obviously. We only considered Nyquist WDM, so we did not consider OFDM or OOFDM here, which is another option. And of course, we now have a factor in between smallest bandwidth and highest bandwidth roundabout of 2, and consequently the maximum reach will certainly also see at least a factor of 2. Again, this is not too bad, because it means I can build a transceiver that in the near field, if you like, supports high spectral efficiency, and if I decrease spectral efficiency, I increase maximum reach. This is a good trade-off. And one slide on what is needed for it. It goes back to my note on the availability of the chipsets for the contenders, by the way, in most cases ran approximately 40 to 50 gigabaud. That means we need another jump in our electronics. And what is necessary there? Well, we need to go from 40 nanometers to 28 nanometers to 20 nanometers. And in the end, we may up, according to these guys who are really great in doing the chips, we may end up with ADCs and DACs doing 100 gigasample per second and more, that may consume a watt or so. And I attended one of the demos at last OFC where they demoed their 40 nanometer 100 gigabit ADC DAC, and it was passively cooled, and they told me put your thumb on it. It's not hot, it's warm. And that was it. It wasn't hot. It was consuming 1 or 1.5 watts. That would have been impossible 3-4 years ago. And we expect further improvements here. By the way, there is one problem. Today they already see that by decreasing from 40 to 28 to 20, the power consumption does not decrease as it did in the past. So they are running into some fundamental limits of today's technologies caused by leak currents or leakage currents. And I guess in order to get here, or maybe even 15 nanometer with ultra low power consumption, etc., they need another quantum leap in electronics. That's a simplified block diagram how then an NSDO 4 carrier coherent dual polarization MQUOM whatever transceiver may look like. It's simply 4 of the structures that I showed on one of the first slides. It's more or less 4 of the structures of the 100 gigabit system. Now, of course, in a way that I can implement here any QUOM or maybe quaternary partial response, etc. that I want, and not only QPSK. So this is an extension of the 100 gigabit systems, and this is exactly more or less the same receiver structure. And yes, this could then do either ultra high spectral efficiency at a few 100 kilometers, or it goes 3,000 kilometers, but at the spectral efficiency more or less of the 100 gig systems. And this hopefully demonstrates how it then could be deployed. This diagram shows the the histogram of the link length in a typical European country. The link length may of course be a little bit longer in the US, and certainly they will be a bit longer for the GÉANT network, for example, but for all the European NRANs, this is likely typical. They are too long for the smaller countries, but anyway, you'll always get such histograms. And if we now apply our 4 carrier dual polarization XQUOM structure to this histogram, we see that we can do at very good spectral efficiency 1 terabit transport, maybe up to 600, maybe only up to 500. We do not know this exactly today, because in the end it also depends on the quality of the respective link. We could do, say, 800 gig up to, I don't know, 900 kilometers or so, 400, even further, and after that, well, we'd have to switch to more or less standard 100 gigabit transport as we'll deploy it from now on. But an integrated 4 carrier, if 4 is the number, even that is still a floating target, but if 4 was the number, then such a structure could do this job flexibly. It could provide flexible spectral efficiency, flexible maximum reach, and hence I think it can support many applications. This is the last but one slide. Now that all the schemes for 400 gig and 1T use different, well, they use different numbers of subcarriers in some cases, different baud rates, different analog bandwidth in the end. In order to support them efficiently, in order to achieve good total capacity of your networks, you would need in the end a flexible grid switching or ROADM structure. And this is just one slide showing the development of ROADMs over time. They started more or less with fixed add drop, so it's a fixed reconfigurable OADM, which may be a contradiction in itself. Well, they started with static WDM filters in the add drop path. Then next was they were made directionless by means of another switch here in the add drop part. They also were made colorless by combinations of by the way, WSS is wavelength selective switches. And the next and pretty major step was or is, we are exactly there right now, to make them contentionless. What does that mean? Consider this structure. I could connect here any color, which is good because I'd like to connect tunables, make it all a bit more flexible. I could then add and drop it to and from any of the line ports here. But what I can't do is, in this structure, I can't add and drop red that would go here and another red that is, I don't know which wavelengths exactly. Would have to calculate in the back of my head, and that's where I'm bad in. I couldn't do the same here, and that would be what we call wavelength blocking. Although the transport capacities in the trunks may have been there. And of course, such wavelength blocking in optical cross-connects and similar structures isn't good. So, and this is solved in contentionless ROADMs. Of course, they are a little bit more complex here, but now they are wavelengths blocking free. Good. And the next step would have to be, in order to be perfectly future safe or future proof, to make the same structure also gridless or flex grid. That means by means of a suitable switching technology, I can vary the bandwidth of my add-drop ports. And first technologies for this exist. Yes, that's the good news. By the way, today the structure of everything of these four would be extremely complex. That's something to be done in the next 1 or 2 years, I guess. And a respective spectrum then could look like this. So we have a number of channels here that take 200 gigahertz. These may support 1 terabit or so, or 400 gig for the long reach. Then we have some that only have 50 gigahertz, and so on and so forth. And that would be then the next generation of, well, the photonic phi, the ROADMs. Conclusion, with the 100 gig coherent, we are unfortunately already at the more or less at the optimum of capacity times reach. In order to achieve drastically higher reach, drastically higher capacity at more or less same reach, there's almost no option. We need completely new fibers, because as I showed, FEC wouldn't work. New amplifiers, etc., would give us 1-2 dB. That's too little. And hence we would need completely new fibers. I put here pure silica or photonic crystal. What is in fact discussed today is multi-core fibers, or maybe few mode fibers. But photonic crystal could also be a nice candidate. Zero nonlinearity, zero PMD, possibly refractive index close to 1, so they are fast fibers. Let's see. Flexible modulation would support adaptation with regard to capacity and reach. And yes, in the end, we need new ROADMs. That's it. Thank you.
Thank you, Klaus. Very forward-looking slides. Any question from the audience?
None.
Well, then I have one, actually two. You shown us very forward-looking things, but can you give us timelines? I mean, when we will see 400G, when we will see 1 terabit, when we will see this flexible, contentionless.
Yeah, there was a timeline in the table. That's the one thing. The other one, of course, would be the I think these are optimistic. The same thing I said here 1 and 2 years ago. At 1 or 2 years here, I would say, and another 1 or 2 or 3 here, and we will meet reality. That's nothing against Fujitsu, by the way. The components guys are always a little bit optimistic. That's the one thing. It won't be possible earlier. And the other one is, well, when do we need 400 gig? Well, when will we have 400 gig clients, 400 gig tributaries? That is the next thing. If I remember all the things about data centers, etc. correctly, we might see it in 5 years. Or starting to see it in 5 years, yes? Remember Bob Metcalfe's talk at OFC 2 years ago? He was desperately urging us to go and develop terabit transport because he predicted it'll be there in 10 years. Yeah, I tend to agree. It's not too far away.
Thanks. All right, if no more questions, then I will invite Jeff to... And whilst he's wired up, just can I see a show of hands? How many things that in the next 4 years you will need 1 terabyte? 1 terabit?
Great.
Come on.
Thank you.
I think then I will have to show my hand. All right. Well, let's welcome Jeff Bennett from Infinera. He got a nice description of his work in the last 25 years, but I think he has seen everything: IP, ATM, DWDM, and I think he will give us now a nice view of how Infinera sees the future. Please welcome Jeff.
Thanks, Otto. Morning, everyone. So let me get right down to this. Some of you may have seen a paper in IEEE Communications magazine in January. It's going to be one of these seminal papers that you'll see again and again and again, a bit like Emmanuel de Sevilla's paper a few years ago on optical fiber limits. Internet demand set to grow by a factor of 1,000 over the next 20 years. Now, how did they get that conclusion? It was, as Klaus said, so you said 50%. They were assuming 40% compound annual growth rate. It's the same thing. The error bars on annual measurements for internet traffic are enormous. So when somebody says 40, somebody says 50, it's a miracle that they're that close together, actually, in terms of agreement. So that's how they got the factor of 1,000 over the next, actually it's about 21 years if you work it out. This is a table from the paper, and it shows a variety of technologies that are then required to meet that demand, 1,000 times growth over the next 20 years. And what the authors managed to do here is to work out an effective capacity multiplier for the different strategies to increase capacity in today's networks. And the largest bang for the buck is actually an increase in spectral efficiency. So this has a 10 times capacity multiplier. The biggest other one is 3 here, and that's using up the excess capacity in today's networks. Things like removing wavelength blocking, removing muxponder blocking. Muxponders are a terrible thing in networks. They lead to massive inefficiencies in the network, and by removing those kinds of inefficiencies, you could maybe get a factor of 3 improvement. But if you want real bang for the buck, you've got to go for spectral efficiency increases. So what I'd like to do, I'm not quite sure about the mix of the audience, and the original committee suggested that there might be some value in pointing out the requirements of a transport layer. A lot of people tend to think that this is the internet. It's a series of IP core routers, service access routers. I don't know how many people saw Pradeep's keynote a couple of days ago. This is exactly the kind of thing that he was describing in terms of internet architectures. Underneath, because router guys always draw these as black lines in between the routers, and in fact, what exists underneath is a transport network consisting of OTN for sub-wavelength switching and grooming, WDM for high-capacity transport, and then the interconnect between the various routers actually tunnels its way through this transport network. So when we talk about increasing spectral efficiency, we're talking about increasing the efficiency of these links down in the transport layer. The metric that we could use is total fiber capacity. Very simply, the data rate of a single wavelength multiplied by the number of wavelengths on that fiber. And we're assuming, of course, C-band. The other alternative that we have, just find more spectrum. Either extend your C-band from a 4 terahertz C-band out to a 5 terahertz C-band, go to the L-band, go to the OE and S-bands. Amplifier technologies don't really work there at the moment, but these are all options for us to achieve a massive increase in fiber capacity, total fiber capacity. So how has the optical transport industry responded to these challenges compared to other industries? And if we look at spectral efficiency in terms of bits per hertz on the vertical axis over time, various other industries like voice band, modems, microwave radio, Wi-Fi and WiMAX on a per site basis have done pretty well. And it's really because of the advances in electronic processing over the years. Digital signal processing, very large scale integration that was available in the electronics industry since the 50s. So they've done well. If we look at the optical industry, to be fair, we started relatively late. The advent of DWDM in the mid-90s, and then but the slope of the curve is actually pretty competitive. We're catching up quickly to these other types of media. But as Klaus said again, optical fiber is a non-linear medium. There are some challenges in trying to maintain that growth rate. But a series of advances have done pretty well. I won't go through them all here. Now, since the advent of WDM, so the mid-90s, we've tended to focus on a series of technologies. One is intensity modulation, direct detection, and the ITU frequency grid. So the whole industry has tended to focus on these areas. What's changing, what changed over the last couple of years as we broke the 10 gigabit barrier. That 10 gigabit barrier was incredibly tenacious. It's been very, very difficult to move beyond a practical 10 gigabit per second per wavelength data rate in transport networks. But what managed to smash that barrier was really phase modulation with coherent detection, the miracle of coherent detection. It's an incredible technology. And unfortunately, we're still tied to this ITU frequency grid, and there are some reasons why that's a bad thing. If we're focused on achieving additional spectral efficiency in fiber, then we need to look at that ITU grid and see what we can do about it. So, what do we have to change? We're going to move to higher order modulation. We're going to be moving to coherent wave combining and separation and getting rid of the ITU grid, moving to gridless super channels or flex channels as we call them. So let's take a quick look. And again, I'm not going to talk about this too much because Klaus gave a very good overview of this, of higher order modulation formats. One thing I will absolutely agree on here is that these higher order modulation techniques, they're not a universal good thing. There are pros and cons with moving to higher order modulation. And what we can see basically is that the capacity reach product peaks at really the current modulation formats that people are using, Polmux, QPSK. Now, let me give you a first order approximation as to why this is. Klaus gave a much more detailed explanation. Fiber is a non-linear medium. So if you imagine the phase states here that are contained within these circles, they can have a certain finite amount of launch power into the fiber before you go non-linear. As you add more bits into the circle, then each bit will have less of that power available to it. So the signal-to-noise ratio, the power levels per bit, will actually drop. So that's why we have this effect as you move to higher order modulation, that it's not necessarily a universally good thing. Now, the benefits of advanced modulation, all phase-based modulations generally, whether you're using coherent detection or not, are more tolerant of fiber impairments than good old on-off keying. It's not surprising. I mean, that's an ancient technique. It's almost like Morse code, really. It's been a very, very tried and trusted approach over the years. Now, we can put more bits into a phase symbol. We can use quadrature amplitude modulation, 8 QAM, 16 QAM, and so on, and get more bits per symbol. And if you look at the magnitude of fiber impairments, if you could wrap your arms around all of these impairments like attenuation, chromatic dispersion, polarization mode dispersion, all the nonlinearities, roughly they will scale with the square of the symbol rate. So if you can put more bits into a symbol, then you can offset that impairment factor. Phase-based modulation also allows us to use coherent detection. Now that's the big benefit, because once we can use coherent detection, we can move to very advanced digital signal processing. So the result is what we're seeing today. 100 gig waves and 40 gig waves, of course, can have the same or even better reach than 10 gig NRZ. Now that's amazing. We can put 100 gig on the fiber that we had to reject a few years ago. We may be only able to run 2.5 gig waves over it. It's amazing. But we have a problem. The practical advanced modulation and coherent detection really only get us to 100 gig. I think that's, I think Klaus was saying roughly the same thing. How do we get to terabit waves? And let's rephrase that question. Do we even want terabit waves? Or are we actually trying to achieve a terabit unit of capacity that a service provider can manage in a single chunk, but also has the maximum spectral efficiency? Remember the original objective here, we've got to try to deal with this 1,000 times growth over the next 20 years. So we need that spectral efficiency. Well, the problem with a single carrier terabit wave is, if we look at this simplified coherent detector, this is actually a super channel detector, but we see these ADCs, the analog to digital converters. Now, we know that we are going to require quantum leaps in electronics. We're going to require these breakthroughs in very high speed ADCs. How is the component industry reacting? Can we actually build those kinds of components? So let's take a look at this chart. We have on the vertical axis the optical signal to noise ratio penalty. I'm not really going to be talking much about that because what we see is we have an increasing penalty as we move to higher order modulation. That is not the point that I'm making on this chart. As we increase the number of bits per symbol, we can actually lower the sampling rate for an individual analog to digital converter. So starting at Polmuxed BPSK, we have a 640 gigabaud symbol rate. That's not the sampling rate, of course, because of Mr. Nyquist. We have double that sampling rate. Polmux QPSK, 320 gigabaud. As we increase the modulation complexity, we can lower that baud rate, but we're getting to ludicrously complex modulation that will reduce our total reach. Where is the component industry? Again, this somewhere in 2014 they might be here, which is way off the chart. So we can't really expect a single wavelength terabit channel anytime soon. So as an alternative, for the foreseeable future, these terabit units of transport capacity will probably not be built. I'll say probably because you never know. Maybe somebody will have a breakthrough over the next couple of years. It does not seem likely. And given that the multi-wavelength approach is the practical option, then we could start asking questions. How many waves? Now we know that the 100 gigabit per second Polmux QPSK, we've already reached the optimum spectral efficiency. And if we can just have lots of them, then we're in good shape, right? We can achieve terabit units of capacity. We just have to manage lots of 100 gigabit waves as a single administrative unit. So in order to do that, we need to change some things. I'm going to look here at coherent wave separation and the idea of getting rid of the ITU grid. But historically, this is the approach that we've taken so far. DWDM direct detection, NRZ with it's a very simple encoding scheme. What we do here is we've got a mixture of signals, mixture of wavelengths here on the left-hand side coming in on the fiber. Our photodetector technology is wideband. If we allowed multiple WDM signals to fall onto a photodetector, we just get noise, right? We just get a garbled signal. So wavelength demultiplexing, as has been done since 1995, that was the original WDM technology, this wavelength demultiplexing simply spatially separates the waves so that we only have a single wavelength falling onto a photodetector. That means we need spacing on the fiber so that we can optically separate them. The optical separation technology has got to be able to get between these waves. But the advantage of this is we can use a very simple modulation technique that almost directly converts photons back into ones and zeros. It means we can have a very, very simple detector. That has been the state of the WDM industry since 1995. Couple of components in the detector, very, very simple. The breakthrough as we move beyond 10 gigabits, from say 2010 from Practical Systems with 40 gig and 100 gig technology, we still retain this spatial separation. But now instead of a simple direct detector, we're moving to a local oscillator. We can drop in the right color. We can drop in the right color local oscillator, or we tune our local oscillator to the right frequency. And that allows us to very precisely pick up the wavelength we need and pass it into this much more complex and sophisticated signal processing circuit. So we use coherent detection to achieve greater reach at higher data rates for these conventional systems. But those conventional systems are still tied to a grid-based wavelength demux architecture. Now this is the current state of the art. And it's fantastic because it does allow us to run 40 gig and 100 gig over fiber that we've previously only used for 10 gig. How do we move a bit further? Well, the inefficiency that we see in the grid-based approach is that between each wavelength there is a guard band. Now, we may have thought we needed those guard bands a few years ago, but ideally we should be using smaller grid spacings. I mean, we use 25 gigahertz grids, but you know, most of the industry is locked into this 50 gigahertz grid because of all optical WSS ROADMs. Now, a way to think about it is that those guard bands were there to allow an individual wavelength to be optically demuxed. Is there a wavelength separation technology that doesn't require those guard bands? The answer is yes. It's coherent wave separation, and the way it might work is something like this. We start here with super channels. So these are waves now that we've actually scrunched together. We've squeezed them together and removed the inter-wavelength guard bands, and we still have guard bands at the edges of this collection of waves to allow us to optically mux and demux the collection of waves, the band of waves. But the band itself has multiple subcarriers. It has these multiple waves. So what we might do with this super channel detector, we start with the collection of waves coming in. We separate the polarizations. In a complex optical circuit here, we'd have multiple local oscillators tuned to the relevant wavelengths. You can do this with a single local oscillator. Lucent have published papers on this. You end up with the separate wavelengths here. Each wavelength is operating with multiple phase states. Could be Polmux QPSK, or it could be QPSK, it could be 8 QAM, 16 QAM, and so on. So you can imagine this is a pretty complicated optical circuit that does this. But the benefit is that we can now get rid of the guard bands here, and the net increase is about a 25% in usable increase in usable amplifier spectrum. So if you had a 4 terahertz C-band in your amp chain, you've now got 25% more of that spectrum being used for actual data. If you could move to a 5 terahertz C-band, you get another 25%. So you could effectively increase capacity by about 50% by doing this kind of thing. Now, our approach, some of you may be aware of Infinera, we build large-scale photonic integrated circuits. It's the thing we do. It's the key to our technology. And of course, I am going to say large-scale photonic integration is the key to economic terabit networking. But the argument that I would use here is that if we look at coherent wave combining and separation, instead of now a single wavelength coming into the local oscillator, we actually have a series of closely spaced waves as a superchannel. And instead of a single local oscillator, we now need multiple local oscillators. The mixture of waves on the fiber is actually grouped into those superchannels with a guard band between the superchannels. And when a superchannel is actually detected, because you could have superchannels expressing through the network and they're not detected, but if you want to add and drop at the superchannel level, you allow the superchannel to fall into onto this optical mixer circuit. Multiple local oscillators do the polarization separation, the wavelength separation, the phase separation, and eventually, for example, for a 10-channel superchannel, 10 wavelength superchannel, you may have 8 photodetectors per wavelength, 80 photodetectors for the superchannel. That's just an idea of the complexity of the optical circuit here. Analog to digital converters and DSPs. The ADCs are operating at today's data rates. They're not operating at some, imaginary future sampling rate. We can actually build this stuff. So, as you want to fill the fiber, you now need multiple super channel detectors. The number of optical components here is exploding. It's absolutely exploding in this kind of architecture. But the benefit that you get is the super channel approach essentially moves your C-band capacity across about 25%, purely by going to super channels. Now, one of the things that you can think about is, what is the right modulation technique? Is it QPSK? Is it 8-QAM? Is it 16-QAM? Now, it's none of them. It depends. It depends on your particular requirements for a combination of capacity and reach. Now, this is the kind of circuit for a Polmux QPSK transmitter. What we see here, the upper part of the circuit deals with the X polarizations, the lower part, the Y polarizations, TM, TE, whatever you want to call them. And the Super Mach Zender arrays, you have the upper and lower portions dealing with the real and the imaginary and the real portions of the phase constellation. What would happen if you needed more reach than Polmux QPSK could give you? In a submarine system, for example, to close a route across the Pacific Ocean, answer, you use BPSK, which will give you more reach. Now, if you were running this circuit in BPSK mode, you'd effectively switch off half the circuit. Now, the point is, you don't make that decision. You don't switch between BPSK and QPSK every day. You do it when the board is installed, and you leave it that way for the next 10 years that it runs. Now, it's very tempting for a product manager. If you were building that board, you'd say, gosh, if I'm building that from discrete optics, why would I put twice as many components in as I actually need? So there will be a strong temptation for manufacturers to have multiple product codes, and here's your BPSK board, here's your QPSK board. Now, a PIC-based design costs the same amount of money to produce no matter how much of it you use, in exactly the same way that a 4-core CPU costs Intel the same amount of money as a single-core CPU. That's why their margins are so much higher on the 4-core CPUs. The fact that you may not be using all 4 cores, I don't know if this has got a quad core. Yeah, it's got a Core i5, so we're probably talking about a dual-core machine in here with 2 threads per core. So how much of it is actually being used just to display some PowerPoint? Well, actually none of it, because it's going via the graphics processor. So, the fact that we're not using it at the moment, we've bought it. It costs the same amount of money to buy that CPU. The same thing is true of a photonic integrated circuit. And the result of this is that you can end up with a flexible coherent, or what we call a flex coherent modulation, with a flex coherent DSP and a dialer reach capability in the optical circuit. So imagine you're dialing the modulation technique in here. By default, you might be using Polmux QPSK, and that will give you great capacity compared to the reach. You want to close that Pacific route, you dial it into BPSK mode, you trade off the capacity for the additional reach. In future iterations, you could imagine having 8-QAM and 16-QAM settings on that board and simply dialing in the modulation technique that you need. The end result is that you can get more capacity in your extended C-band compared to lower order modulation techniques. By the way, these are all Polmux. I should have put Polmux 8-QAM in here and 16-QAM. So if you were dealing with an extended C-band, this is an individual super channel within that extended C-band, assuming everything is using Polmux QPSK. And you will have a certain width for that individual super channel. If you could use a higher order modulation technique, it'll be a bit narrower. If you could go to 16-QAM, that will actually be half the width of Polmux QPSK. That all of those red dotted areas are carrying the 1 terabit unit of capacity that we're attempting to achieve. And you're getting more capacity per fiber if you can move to those higher order modulation techniques. The problem is, and there are the actual values that you could potentially achieve. The problem is you don't know if you could use that higher order modulation. You may not have the reach with an 8-QAM or a 16-QAM system, a 32-QAM system. So how would that actually work in a single fiber? Well, if you had to close a long route without any regeneration from A to E, you may even have an interoperability requirement with WSS ROADMs, because they're going to be obsoleted by flex channels. So if you had to interoperate with a 50 gigahertz grid system, you might operate in regular grid-based mode. If you didn't have to have that interoperability, you could go to a Polmux QPSK flex channel, because you need long reach. If you could get away with a shorter reach, like from A to D, there you can turn it up to 8-QAM. Shorter reach again, you could turn it up to 16-QAM. So now all of these are living in the same fiber. They're running on the same fiber. Each individual board that you have, the super channel boards, are software programmed to the appropriate modulation technique. They don't have to have 10 channels, by the way. You could group them into arbitrary numbers of channels to build flexible super channels from 100 gigabits up through to a terabit, all on one chip, by the way. 1 terabit PIC. So in summary, these pure terabit waves are unlikely to become practical in the near to midterm horizon. Now, again, you're asking about timescales. 2014 is a date that we're heading for prototypes of these kinds of things, and we believe it's achievable because we're not looking for exotic ADCs. We think because we have 10 channels in our super channel, your spectral efficiency is just the same as if you had a 1 terabit super channel running with an exotic analog to digital converter, which won't be invented until 2018. So pure terabit waves unlikely to become practical in the near term. Super channels are much more likely, and a flexible modulation technique is essential. Now, if you accept those two premises, then the super channels will be made up of multiple closely packed waves that do not necessarily align on the ITU grid. You could align them. You can simply tune them to the ITU grid if you need backwards compatibility, but you don't have to. A programmable optical circuit will actually transform those super channels into flex channels for maximum flexibility as you're trying to trade off reach and capacity, and minimum spares management. You've got one part number for all the different modulations. So those two requirements really point to photonic integration being a key enabling technology in the terabit age, because super channels, you need 10 channels running at the same time. So why wouldn't you just implement that on a single chip? Why would you try to implement it with discrete optics? It'd be crazy. It's like trying to build one of these laptops from individual transistors, capacitors, resistors. You may be able to do it, and you get a round of applause if you manage to get it to work, but it wouldn't be very practical. And that programmable optical circuit depends on PICs, because you don't care if you switch half of it off or 2/3 of it off or any combination of it off. It costs you the same amount of money no matter how much of the PIC you actually use. Thank you very much.
Thank you, Jeff. Any question? You must have some questions. Come on. Please.
Hello. I understand that the ITU grid now will become, I think, obsolete, and we have to, as you said, abandon that paradigm. But how do you see that interoperates with ROADM technologies for optical switching, path, and so on? The technology to deal with that is ready?
You would probably be better off asking a manufacturer that uses ROADMs. We don't use ROADMs.
Oh, okay.
We perform this electronically. We think everything could be digitally switched. It's a better way to do it. The problem, as I understand it, is that if you're using two-dimensional MEMS for a WSS ROADM, so remember in Klaus's diagram, he had the little boxes with WSS labeled in them for the different kinds of ROADMs. Those are actually quite complicated and expensive optical components. You're looking at like $20,000 a piece for the cost of the component before you manufacture it into a product. So the more of them you have, the more expensive and complex the ROADM becomes. And the problem is they all have to be laid out on an angular structure. And the angle is determined by the grid spacing. So you have to talk to the guys who are making these WSS components and say, what grid spacing are you going to use? And for the last 5 or 6 years that they've been around, they've been using a 50 gigahertz grid spacing. Now, you can put them on any grid spacing you like, but I don't think with that technology, I may be wrong, I don't think you can have it flexible. You choose the grid spacing, and I think there'll be an arbitrary choice of a relatively fine grid, like 25 gigahertz. And they'll say, oh, that makes it flexible. No, it's 25 gigahertz spacing. You know, you can't really flex it. It has to be a fixed set of angles.
Thank you. We have one more question there.
Thanks. Super channels might be a good solution for various things, but you mentioned sometimes, several times, that the gain of capacity is about 25%. I would say 25%, that's nothing. I mean, 25%, we are discussing about factors of whatever, 1,020 years, 25%. Yep. What's that?
Exactly, it's a great point. So it's 25% from the super channel. It's another 25% from the extended C-band operation, and then you double it if you could move to 16 QAM modulation. And that's assuming that you're going to have every single channel in your extended C-band on that same modulation. So you can increase that capacity, but it depends on your reach. Our point is that you need to be flexible with the modulation technique that you use, because some of those super channels will be traveling further than others. What you don't want is a whole set of different part numbers and individual laser-based implementations of this, because imagine, if you try to build a super channel from discrete components, it's going to be very unreliable. All the fiber connections and the multiple components, it's going to be very unreliable. You know, we've never had a PIC failure. We've had 6 years of PICs being shipped, 500 million field hours of PIC operations, not one single failure. PICs don't fail. Thank you.
Okay. If there are no more questions, thank you, Jeff. I'm pretty sure that in a few years' time we will revise this race between optical components and electronic components. But I'm glad that there is some competition between you guys. And our next speaker is from Siena. His name is Rodney Wilson, and he traveled from far away to talk to us about their plans for the future. Rodney is a former Nortel fellow, so please welcome him, and let's hear what Siena's plans are.
Thank you. So I'm the only thing between you and lunch at this point, so I'll be sensitive to that. I work in Siena's research labs, which are in Ottawa, Canada. And Siena acquired the optical assets of Nortel about a year ago, and we've merged the two programs together, and it's been very successful. And so we spent the past 14 months going around, trying different things, speaking to different customers, and moving forward. And so there are a number of lessons learned through these participations and these exchanges. And so what I'm going to do here this morning is talk a little bit about the lessons learned. And the first lesson really comes from applications of optical technology. You know, in the first iteration, we connected places, so you'd make a telephone call. Then you'd connect people, right? So I'd phone your mobile. And now, of course, we're connecting things. And these are creating huge, powerful market forces that are driving our innovation. So the pursuit of technology is really driven by the app. And that's sort of the first lesson learned. And you can see on this slide a number of the the factors that are affecting our customers. Most of our equipment has been purchased by telephone companies, carriers, and communications providers. And when we look at coherent, and actually there was a reference to this earlier on, coherent technology is applied to optics. It's very similar to the comparison of Morse code and simple on-off to digital radio. But the history is kind of interesting because it was 1966 that Nobel laureate Charles Kao was able to prove that you could send communication signals through optical fibers. And he was able to achieve 1 megabit per second over a span of 10 meters. So that was 1966. So 20 years later, the state-of-the-art was actually developed by Bell Northern Research, a precursor to Nortel. And they were able to go 565 megabits per second, a distance of 40 kilometers, and turn that into a commercial product. So it took 20 years, right? So 20 years after that, we were able to achieve 40 gigabits per second in a span of 1,000 kilometers. And it was just 4 years later that we were able to go 100 gigabits per second and 2,000 kilometers. And those are the systems that we're using today, and largely enabled by the use of coherent optical technology. And here's a different timeline showing the capacity scale over time. And as the previous speakers have described, a number of different enabling technologies that help to achieve that. The technology we have that does this is called a WaveLogic. It's our particular chipset that combines these various characteristics to achieve the capacity and scale. Not all coherent technology is created equally. We do use advanced coherent DSPs. We're able to do 6 simultaneous analog to digital conversions at a rate of 20 billion samples per second in a very low power chip. So we're able to combine advanced DSP technology, very high forward error correcting technology, and this high resolution analog to digital conversion to really help power our systems and the coherent technology necessary to do it. So in 2008, one of the lessons we learned, we worked with Supercompute, the large conference in the States. We conducted a number of different experiments. We like to try stuff. Failure was kind of permissible. So in 2008, we did a 100 gig system for the supercomputing conference. The goal was to achieve greater than 8 terabits per second per fiber. And we were able to transmit a petabyte of data transferred in 12 hours on a single carrier. And these are the characteristics of what we were able to use. We had a single carrier, 100 gigabit per second at the 50 gigahertz ITU spacing and the C-band tunable. We used asynchronous multiplexing, if you will, so we had 10 by 10 gig E as a client. There were no such things as 100 gig client interfaces as we have now. We used DPSK, QPSK as discussed previously as our modulation technique, and achieved very low latency and put it into a commercial form factor. So that's one of the things that we learned by participating with this community, and it was very successful. Our partner in this particular exercise was the California Institute of Technology, or Caltech, and so we collaborated with them. They provided some of the content and some of the expertise and so on. And Siena has a practice group that I'm responsible for. Actually, invests money in universities. We are the industrial partner that a lot of universities require to help expand communal knowledge. We take a very novel approach to intellectual property. We allow the researchers to continue to own and manage that IP. but we license it and have rights to use it. So we really feel we're a participant in the research community, and indeed our research labs work in this way. So we had another interesting experiment, which was 100 gigabit Ethernet with 100 gigabit optical, running over 1,500 kilometers of a very mixed type of fiber. So different fiber types, as well as compensated and uncompensated fiber. And you know, when you look at the coherent detection, one of the things you try and get rid of is the rigidity of having to have compensating fiber in the middle of your span to correct for PMD distortion. If you can correct it electronically, if you can correct it in your system, you actually lower the cost and complexity by removing that compensating fiber. But it's out there, and if you're going to implement systems like this, the cost to go out and remove it and retune the fiber is very expensive. So the trick was to operate a system that was flexible enough to accommodate these different types of fiber and very high PMD. And of course, we were successful with that. Our partner was actually Verizon, and again, it was very much an experiment. This wasn't this wasn't a sale. This was a kind of, can we do it? And we could. So the first couple of lessons. The next lesson moved on to really a look at Ethernet. Ethernet both for service and infrastructure. The arrival of 10 gigabit Ethernet really defined Ethernet no longer as a local area network technology. It really became a WAN technology, a wide area networking technology. So with that comes responsibility, right? You know, if your local drop to your laptop fails or some problem like that, it's important to you, but it's not going to change the balance of power in the world. But if you're using it as a wide area networking technology with thousands of users on it, and it fails, then you're seriously impacting the system. So reliability with Ethernet became key, but it is the most ubiquitous computer interface on the planet. So if you use that as a common denominator, and you're able to bring in the service requirements, meet the key goals of it being universal and ubiquitous, it's very low cost. It helps lower the cost of systems, and of course can accommodate multi-rate. So one of the things we learned along the way is to use Ethernet for both service, delivery, and system infrastructure. The next lesson we used is the emergence of OTN, optical transport networks, and using it as a common container. The ability to combine different applications, different traffics, to make best use of this spectral efficiency we've achieving. So as we develop modulation techniques, as we increase the span and so on and so forth, you want to be able to make usable use of that. So there are a number of things that we're able to carry in this way. You see in a fiber SDH and gigabit Ethernet. Gigabit Ethernet, of course, used very creatively for virtual LANs, for creating multiple virtual LANs. SDH Sonnet, of course, is evolving to carrier Ethernet, and so providers, manufacturers like Ciena, have multiple product lines that include now a carrier Ethernet, as well as the optical transport capability. And so in this way, you're able to make very good use of optical transport networks as a technique, as a common container to create best value usages of the system. So OTN enables transport of transparent services. So a lot of what we're hearing about at TNC is the different applications, whether it's applications for storage or applications for digital media. Of course, in our world, we look at traditional carrier transport and the requirement to handle Sonnet or SDH, as well as this ubiquitous Ethernet. What this particular slide attempts to show is that regardless of the type of traffic, whether it's data, voice, storage, legacy TDM, high-definition video, high-definition 3D video, like we've seen over here in the Polish demonstration, all on one platform, all with one wavelength, and really supporting a variety of mixes of different services with a smooth transition to the circuit to packet evolution. OTN, Optical Transport Networks, enables mesh control plane automation. So if we argue that the bandwidth problem is solved, right, so we've all heard about 100 gig, multiple 100 gig techniques up to a terabit and in the future beyond. If you solve the bandwidth problem, how then do you control it? How then do you make best possible use of it? Well, you do that through dynamic provisioning and the creation of automatic control planes. So you can use it for, self-inventory. So one of the techniques is to actually inventory the network topology and the systems within it. If it's self-aware, then it can be used for automated connection management. So to create a light path through a variety of different system topologies. You can use it to increase the efficiency of systems, or if there's a failure, a self-healing of the network. Now the research and education community is doing a lot of work on different control planes, and there are a number of different research initiatives around this. Things like OSCARS, which was led really by ESNet with Internet 2. The OpenFlow experiments are attempting to recreate this at layer 2 and layer 3. Other programs like DRAC, the Dynamic Resource Allocation Controller technology, are all trying to achieve the best use of these mesh technologies. So once they're created, how best to leverage it. So one of the most recent examples of how this mesh technology and the dynamic self-aware network was able to resolve a problem was with Verizon, who have a very large installed base in Japan. And of course, on March 14th of this year, there was the Japan earthquake and ensuing disaster there. But the systems were able to self-heal, even though there were several nodes that were taken out. So this was done virtually instantaneously. It was done without human intervention, and was really able to maintain connectivity both within Japan as well as their transatlantic cables, as shown in the little sketch there. So this whole issue of control plane and making maximum efficient use of the optical infrastructure is important in industry, it's important to research, and it's important to e-science. We've done a number of terrestrial demonstrations. I'm going to highlight 3 of them here. The one that we did last year was a connection between our research labs in Ottawa, and you see the tile display in the picture there. We have a tile display because we participate with Cinegrid and a number of other research groups around the world that's referred to as an OptiPortal. This is based, as I say, in our labs in Ottawa, and we wanted to showcase 100 gig. We wanted to set up a 100 gig circuit. In this case, between Ottawa and Chicago, which is a distance of about 1,300 kilometers. It was an existing 10 gigabit per second system, but we didn't have any additional channels available. So the whole idea was to replace that 100 gig or that 10 gig system with 100 gig using the technologies that we've been talking about here this morning. So we were able to basically pull out the 10 gig circuits and plug in the 100 gig circuit packs. And because of coherent receivers, because of the technology, we were able to establish a link in about 15 minutes. The upgrade required no additional repeaters, no regen, and was simply a 10x upgrade that took a very short period of time. So that was the infrastructure. What about the application? So my challenge to my friends in Chicago at the Starlight Gigapop was, okay, so now we've built a network. What are we going to do with it? What's the application? And they brought in streams of data from 3 different sources. One of them was the National Center for Data Mining. So they do research, huge databases, a lot of astronomical research. They brought in NASA, and NASA's database basically files from supercomputers. And they brought in traffic from the International Center for Advanced Internet Research, which is at the Northwestern University. And so they said, right, we're going to turn on the fire hose. And they started throwing the data into the system. Well, I don't have anything that can digest that in my lab. I don't have, huge supercomputer or a storage. So we just sort of threw the photons on the floor and used our network management systems to show the capacity being used within the system. However, there was one stream of traffic that we did. We were part of a consortium with a number of Canadian universities that have created a unique database of brain scan images. They basically took a human brain, sliced it 17,000 times, and took HD pictures of each layer of the brain. And this is used obviously for neurological research. So the fact that McGill University in Montreal has a database of a brain means absolutely nothing to anyone here, even if you were the world's best neurological researchers in this room, right? Who cares? I'm not traveling to Montreal to look at a slice. So the key, of course, is how do you make this information available to researchers around the world for whom this is a big deal, right? So in order to do that, you need a very high-speed network. That's the application. So in this case, we were able to connect our to the database in Montreal. We connected that through another high-speed circuit from Canary, the Canadian Research Network. Brought that to Chicago, and then we're able to route it through our experimental 100 gig light path, and then use it in our lab in Ottawa as part of our demonstration, as part of our proof. So not only did we fill a line with kind of meaningless traffic that I'll never understand and data we could not use because we don't have any way of processing it, but we also brought in this research. And the research was quite interesting because basically developed an elevator shaft that would take you to whatever layer of the brain that you want. And some of the physicians were explaining to me, say, well, this layer here is where we think Alzheimer's happens. And the only way to prove someone has Alzheimer's right now is a post-mortem slice of the brain. But if we can find out why this particular piece of the brain changes with this disease, then we'll really have a diagnosis for this terrible disease. And since that time, which was last November, actually groundbreaking work was done with this in the UK, based on access to this database in Montreal. So there's a really cool app, right? Another interesting demonstration was to support petascale computing, which is a demonstration led by NASA at last year's Supercompute. And they created a test bed network that would pass light through a variety of different switches. One of the nice things about working in this community is often there's huge collaboration between all the vendors. Certainly Infinera and ADVA and Sienna, Juniper, Cisco, and others collaborate together at the Supercompute show to actually facilitate the creation of the world's fastest network for 1 week for researchers, for this community. And that's certainly what we did with the 100 gig network technology for petascale science last year. My last example is what we're doing here at Torina. We've created a light path that basically goes from CERN through Amsterdam to Copenhagen. And when we were doing our planning for this, you'll see the map isn't quite accurate. Copenhagen is not up there. We were trying different routes. How far could we go? This is an experiment. We didn't know if it would work. Our original stretch objective was to go to Stockholm. And we said if we could drive using a 40 gigabit BPSK modulated system, we should be able to prove connectivity through to Stockholm. But in actual fact, we capped it at Copenhagen, not so much because of the technology issue, but because of the capacity issue. There wasn't a spare fiber dark fiber that we could play with on the undersea route, and we would be interrupting existing traffic. So I just typed in sort of the termination 2. No, we didn't get there. We just terminated 1 in Copenhagen. It's a pretty interesting system because it covers 37 spans of a variety of different fiber types. And the last span is a foreign wave between Hamburg and Copenhagen, done with our colleagues from Alcatel-Lucent. And so it's a foreign wave through their system, tunneled through their system. So that's the infrastructure. The application is actually being done by the University of Amsterdam, and when you break for lunch, I'll give you an invitation to visit our stand over here. You can see the performance of this link, which is being used for different protocol techniques as we try and optimize TCP/IP or UDP for low latency solid state drive transmission. So we're trying to maximize throughput on a high performance system with lowest possible latency. And that's research that you heard about a little bit at yesterday's plenary with Dr. Kees-de-Laat. So what's the future? I think my colleagues have done an admirable job of describing the future. Very simply, we have 3 different levers that we can pull, 3 different axes, if you will. One is to increase the symbol rate. One is to increase the baud rate, or the constellation of carriers, and one is to multiply the subcarrier and multiplicity to create these super channels. And in actual fact, the answer is going to be a combination of all 3. So if you can exploit all 3 of these dimensions in order to optimize spectral efficiency, performance, and of course cost and reliability, then you have the solution necessary to take you to a terabit and beyond. Last year we successfully demonstrated a terabit per second per wavelength using 160 gigahertz spacing in our labs, and throughput of 1.12 terabits per second at 6 baud samples, 6 billion samples per hertz. So so that's in the lab. It's not ready to go anywhere. It's demonstrated and working. And that's pretty much the state of the research. And that's pretty much where everyone is. And you'll see different vendors trying to manipulate the levers in different ways, and we'll all try and optimize it. Ultimately, it's a mixture of all 3. And we've had fabulous success with our coherent receivers. There are over 7,000 deployed in networks around the world. But if I go back to my first slide, I know what the drivers are. Most of our systems are installed by carriers. But in this space, the challenge and the question to you is, what's your app? If the bandwidth problem is solved, what is the requirement to fill a terabit per second? I know that millions of cell phone, millions of high definition transmissions and so on are going to push the bandwidth requirement up, but that's an aggregation story, right? So I know how that works. I know all the economic drivers for that. Everybody, right? But in this community, this e-science is really the only place where people can try and fill a single 100 gig or a single 40 gig, dare to say a single terabit, with a single flow. So the challenge to you and the question is, what is the app? And on that, I'll leave my presentation. Thank you.
Thank you, Rodney. So let's live up to the challenge. What is your app? Anybody?
No takers just yet, right? I'll go back to work then.
Any question from the audience to Rodney?
See, I gave you that lunch warning thing, right? So.
Yes.
Okay, thank you very much.
Okay. Thank you. Before you leave, everybody, just a few announcements. That if you haven't taken your gift, please go to the Terena booth. Show your. You have, I think, a paper, and you can collect your mini camera. And for tonight's gala dinner, some historical trams will live somewhere from nearby, but they will not wait for us because they are in the traffic. So please be there at 6:45, and somebody will take us to the tram stop. Also, to be there, there will be beer on the tram. So come on the tram. There will be nice trams. There will be free beer. Come on. Okay. Lunch. Thank you.